Hello everyone, we're starting a free open lecture in our Discord. All our lectures are held weekly without interruptions. If you, the viewer, want to ask questions and get answers in an online format, join our lectures. You can find the link to the Discord in our Telegram channel. To find out the schedule for the lectures, join our Telegram channel. Today, we have the G3 Diva problem. The problem is called tree destruction. The time limit for the test is 2 seconds. The memory limit is 256 megabytes. Given a tree, you can choose two vertices A and B, and all the vertices on the path from A to B are included, including A and B themselves. In this case, A can be equal to B, that is, it can be from there the top two in total. So what you need to do is find the maximum number of connectivity components that can be obtained after removing the path from the tree. That's how it turns out. Constraints range from 10 row 4 to 2 10 row 5 strict on n. Each test gives a single number. Basically, if we summarize, we have a tree with n vertices. There are n vertices and n edges. You need to choose vertices A and B, and they can be the same vertex. On the path between A and B, all vertices are removed, including themselves. You need to choose these two vertices in such a way that you get the maximum number of connectivity components. You need to output their count. A connectivity component, well, in this situation, it's the number of trees we will get, meaning that after removing the path, we will have a forest of trees, and we need to find the largest possible forest so that there are as many separate trees as possible in this situation. So let's go through some examples. Well, let's say we have a tree that looks like this, like a bamboo, and then there's a small branch. Here are the designations right away. The green ones are the vertices that remain after removing the path. The purple ones are the vertices that we will choose. These will be A and B. The red colors indicate what to remove, which is connected to the purple ones. Well, it's clear the highlighted ones are also removed, but for such a tree, the optimal way would be to remove everything between vertices 3 and 2, including the vertices themselves and the choice between them. The educational part, well, the three components will be vertex 4, vertex 5, and vertex 1. Well, that's that. There will be three. Next, let's consider this example, where we have 6 vertices that are not connected in this way. The optimal choice for the vertices would be to select 1 and 3. In this case, we will have 2 free components on the side of vertex 3. The sides of 1 are also 2, so we get 4 more. You can't really survive here, but basically, if we have 2 vertices, the maximum can be 4 out of 6. And the last example, we have these legs, a body, so to speak. That's how the tree turned out to be drawn from 6 vertices. What would be optimal here is to choose vertices 3 and 4 and the path between them. Go ahead, remove everything. So it turns out that vertices 3, 2, and 4 are removed. Vertices 5, 6, and 1 will remain, each of which will be separate connectivity components. So the final answer turns out to be 3 for this example. So then let's visit and move on to the solution. So the first thing I'll point out right away is that we will only suspend, well, we have a tree here. As you can see, Loganin is not suspended by anything, not even by 1. What we can choose ourselves. Even if it were suspended, we could change it however we want. For convenience, it's better to suspend the tree from a vertex that is not a leaf. That is, one that has more than one neighbor, so to speak, more than one adjacent vertex. This is, let's say, such a graph, such a tree. What can we suspend it from here? In fact, only from vertex 2, because both vertex 1, vertex 3, and vertex 4 will have only one neighbor, meaning they will be leaves. And vertex 2 will have as many as 3 neighbors, so it won't be a leaf. It's like right away, it will be a little, but even while I was solving the problem, it seemed to simplify a lot of things. Because if we have, well, in theory, we can say that we can suspend it from there, or was her answer not the most convenient way to read it? So moving on, what can be noted here is that this is dynamics on a tree, and in essence, accordingly for this dynamic, we ultimately get 4 arrays that will in total solve 2 subproblems. What arrays do we have? And to the maximum, what subproblem will this be? Maximum dpit will be equal to the maximum possible answer to the given problem if both selected vertices A and B will be located in the subtree with root at A. There will also be an array called big sub. Big sub. This will be the maximum number of connected components that can be obtained from the subtree with root at A if one of the selected vertices is in it and the other is not. So conditionally, we chose vertex A in this subtree, while vertex B will be located somewhere outside of this subtree, and it will learn from A through our tree and go along the chain of removable vertices. We will count how much this will result in. The connected component is below. I'll show you the drawings. How is this going to happen? Well, X and U, those are the two largest big subs among children. We will need the vertices to calculate the recurrent forms, meaning we will keep track of the two largest values for each vertex. Vixap among children too. With this thing, the level of paint is in that choose our numbers, A and B. So for example, it will be shorter here, like an axe race. Here, potentially for the subtree, let's consider how this will actually happen. Oh, let's say we have this scary thing. From 15 vertices, we need to find the DP for the empty vertex. In fact, what you have is the DP, and there should be some path passing through vertex 6. Under the tree up to 6, so this is the urgently needed maximum possible answer under such a condition. Here's how the optimal option would be to choose two vertices A and B inside the tree, completely up to 6 in the tree. Here, this is something, and let's hang it on 1 and lead it from top to bottom. And this will be the tree completely. Will you have any answers here, and which vertices are in this subtree and which ones are relevant? But which vertices? If you remove any vertex, it will immediately fall off. Among the children, there are many connected components. Which vertices will these be? These will be the vertices, namely 13 and 6. So if we remove 13, we immediately get these two connected components. Well, and plus this one at least appears right away. And then it depends on how we continue the path. With 6, the same thing happens. At least two components appear right away. Therefore, these two peaks are not as if they can be social at once, but rather as is possible here. That is, in fact, this very ki option will be one of the cases of the optimal choice. We remove 6, 13, and 7. What connected components do we get? 15, 1489, and the cake on top become separate components. The answer for 6 is 6. From where we started, we can still choose. We can either choose 10 or 11, and we will also get 6. And here, from which I started to make, here you can still choose, well, basically either 10 or 11, and we'll also get a 6. After all, we can either choose a vertex in the summer, and we will still have up to the call for the skip. And I showed this subtask. So the answer for the subtask with Big Sab is that we need to proceed. We have to choose some vertex, and here we need to look for a mix-up for vertex 1, 2, 1. So our answer should be for the subtree with vertex 1. We need to choose a vertex in such a way that, for example, we choose 8 like this. So everything was removed. And as a result, we got the maximum number of connected components. So actually, this is the question that Big Sab should answer. For such a subtree, how can we do this? Which vertex should we choose, starting from which we will go to 1, remove all these paths, and get the maximum number of connected components, which is 6. We color the 6 and remove it like this, and we get how many connected components? 1, 2, 3, 4, 5. Well, I can see that there's no way to survive here anymore. There's no way that our development is happening like this. I need to use it. If we don't dual the 6, it won't be used. The answer is 5. Coloring is like that. One way to choose a vertex. So the final answer will actually be 5. Well, yeah, it seems like the coloring is just like that. Basically, there was one way to choose a vertex, X and Y. They are not distributed separately.
Want to become a great programmer? Subscribe to our Telegram channel.